Imagine 6 months from now, a customer says that your AI system gave them a recommendation that caused real financial damage. They are not asking how your model works in theory. They are asking what exactly your system saw, what documents it used to generate the response, and whether the same answer would be produced again today. In many AI systems, the honest answer is that we have no idea. We might have logs, we might have CloudWatch traces, we might have some prompt code in GitHub, but we cannot reconstruct the actual decision that happened at that point in time. So real question is whether your AI is defensible or not. Can you prove what happened? Can you explain it? Or can you reproduce what was produced at the time? That is what this video is all about. We are going to build an auditable RAG system where every answer is traceable, reproducible, and backed by evidences that can stand up in compliance or legal reviews. In traditional software systems, correctness is simple. You give the same input, you expect the same output. If that doesn't happen, something is broken. With LLMs, the same input can produce different outputs depending upon various factors like temperature, model updates, prompt changes, or even subtle retrieval differences. So correctness can no longer mean determinism. Instead, correctness in AI systems become about accountability. It becomes about whether we can explain how a decision was made, whether we can show the evidence that was used, and whether we can reconstruct the reasoning process after the fact. So when we talk about system correctness for RAG, we are really talking about three things. Traceability, meaning every response can be linked back to its exact input and source. Second is reproducibility, meaning we can replay the same decision path using the same versions. And the last one is audit integrity, meaning the records themselves cannot be silently altered. So let's learn how we can make our RAG system auditable. The most important architectural concept in this entire system is the separation between online plane and the offline plane. The online plane is the serving path. This is what runs in real time. An API receive a request, performs retrieval, runs the language model, and returns an answer. And we write an audit record. This plane is optimized for latency and reliability. It must respond quickly, it must not block users, and it must handle failures gracefully. The offline plane is where correctness actually lives. This is where we manage prompt versions, model versions, indexes, document ingestion pipelines, and audit analysis. This plane is optimized for governance, but it's not optimized for speed. The only reason we are talking about online and offline plane is that if you try to solve correctness purely inside the online plane, you will fail. You cannot retroactively construct decisions unless the offline plane is already storing the right metadata and lineage information. So the online plane produces evidences and the offline planes make the evidence meaningful. Today, we are going to build an auditable RAG system using Python and LangChain on AWS platform. But before that, let's first walk through what actually happens for a single request. A client sends a question to our API. The very first thing we do is generate a trace ID. That trace ID becomes the identity of this entire decision. The request flows through authentication and validation. Then it enters the RAG service, which constructs a retrieval query and sends it to vector store. The vector store returns a set of top K chunks. Each chunk has a stable chunk ID and metadata linking it to the source document. Those chunks are injected into a prompt template. The prompt template has a version as well. The language model is called with a specific model version and generation parameters. The model then produces an output, and that output is returned to the user. And in parallel, we construct an audit record that captures every one of those steps in a structured form. The trace ID ties everything together. Without that ID, you don't have a system, you just have logs. So the question is what must be logged for compliance? Logging only a response or prompt or just tokens are not enough. A defensible audit record must contain the raw user input, the exact prompt version, the exact model version, the retrieval configuration, and the chunks IDs used, and also the final output and enough metadata to reconstruct the full context of the decision. It must also include timestamps, actor identity, and ideally cryptographic hashes so you can detect tampering. The key design principle is that the audit record must be sufficient to replay the decision without relying on any external system state. If you delete your vector index tomorrow, your audit record should still tell you which chunks were used. If your model provider changes weights maybe next month, your audit record should still tell you which version was called. In other words, it should be a complete forensic artifact. Now, the question is where LangChain fits and where AWS fits in this context. As we discussed in the previous video, LangChain sits inside the online plane. Its job is to orchestrate decisions. It builds prompts, executes retrieval, and invokes models. It understands the semantics of your AI workflow. AWS sits outside that logic. Its job is to enforce system guarantees, identities, network isolation, encryption, durability, access control, retention, and immutability. Now, let me show you what we are actually deploying with CDK. This CDK stack creates three logical areas. One is the ingestion pipeline. The second one is an audit subsystem. And the third one is an online query API. So let's start on the ingestion side first. Ingestion side provisions an S3 bucket where the documents land, a step function, which is a state machine that orchestrates deterministic chunking and idempotent upsets, DynamoDB tables that store document metadata, version metadata, stable chunking, and doc version to chunk mapping records. There is a version table here as well, which is not shown in this diagram because the diagram is optimized for flow, not for DDL accuracy. The very first bucket here is the document bucket. This is where the raw source document land under a prefix like uploads, /uploads, and then our text files. It's a versioned bucket, so every overwrite creates an immutable object version history, which matters because we want our ingestion version IDs to map cleanly to S3 object versions and make what changed when a first class concept. The bucket is also what triggers the ingestion pipeline. When a new object is uploaded, an S3 event notification invokes the ingestion lambda, which starts the step function workflow. Now, the second one is our artifact bucket. This is where the pipeline writes derived assets. Most importantly, the per version manifest files that records exactly which chunk IDs were produced for a given document version. These manifest files are your proof artifacts and your replay artifacts. They let you show in a single JSON file the stable identifiers that connect a source document version to the set of chunks that the online plane will use. In the offline ingestion plane, let's look at our DynamoDB tables. So the first one is the documents table that stores one row per logical document keyed by doc_ID, and it holds the metadata like the S3 key, the latest version pointer. It doesn't store all the versions of a particular document. It just stores the latest version ID and pointing to the S3 document. The version table stores one row per document version because one document can have multiple versions depending upon the changes made to it. The version table is supposed to store all the versions of that document. Wherever the document table stores only one row per logical document with only latest version ID. So let's move on. Next one is our chunks table. The chunk table is the core of idempotency. Each chunk is keyed by chunk ID, and the chunk ID is a deterministic hash derived from the doc ID and chunk text, which means if the same chunk text appears again in later version, it will produce the same chunk ID and the upsert will land on the same DynamoDB item. That is the entire trick behind preserved chunks. If the content is not changed, the IDs remain unchanged as well. Next is doc chunk table, which is this one here for the mapping. It's a mapping table that ties it together by storing for each doc ID and version ID the full ordered list of chunk IDs that were produced. Next is the third bucket, which is the audit bucket here. This is the source of truth for online decisions. Every question-answer interaction writes a structured audit JSON file into this bucket. In a production variant, you would enable object lock and retention policies here to make the audit trail tamper evident. We store the full JSON audit record to audit S3 bucket and writes a smaller index record to audit index table, so we can quickly find the audit S3 object later on by trace ID. This two-store approach is intentional. S3 is your immutable ledger and DynamoDB is your search index. When someone asks what happened for trace ID X, you query DynamoDB table in milliseconds and then open the canonical JSON in S3. Now we get to offline lambdas. The Common in env, this block here is just a way to pass resource name into Lambda consistently, so the code doesn't hard code table names or bucket names. The ingestion router Lambda, which is our first Lambda, is the entry point of the whole system. It is triggered by S3 upload event, and its job is to register the document and the version in DynamoDB, and then start the step function workflow to do all the heavy lifting work. You can see it's a small Lambda with memory size 256 because it is only doing event handling and then pushes the heavy workload into state machines so that we can easily observe the outcome. Next is our chunk and upsert Lambda function, which is here in the diagram. It's where the deterministic processing happens. It reads the document content, chunks it, compute the stable chunk IDs, and then idempotently upserts chunk records. The function is sized larger, which is 1.36. That's because it's doing the real work. It's embedding, parsing, writing multiple items. It generates embeddings for every chunk and indexes those vectors into Amazon OpenSearch serverless, which is what we are using for our vector database. And then the online plane here embeds the query and performs k nearest neighbor search to find the relevant chunks. Next is our build manifest Lambda. This produces the artifact that makes the whole system defensible. It reads doc version to chunk mapping and write the manifest file in JSON format into the artifact bucket. Here we then create a vector search collection, which is the managed OpenSearch serverless flavor designed specifically for KNN vector queries. We add two security policies. One is encryption and the second one is network. Encryption policy is something that currently uses AWS managed key for the demo simplicity. It should be something like your own customer managed key, but for now I have just used AWS managed. Then comes network policy, which is allowing the public access so the Lambdas can reach the cluster without any VPC endpoints. That's also for simplicity purpose. In production build, the network policy is the first thing I would tighten. The next piece is index creation. OpenSearch serverless collections exist without an index until you create one, and we want it to be automated and be created at the deploy time. So we add a small custom resource, this Lambda here, with this name, and we wire it to CDK custom resource. When the stack deploys, that Lambda runs once and create an index called chunks if that doesn't exist. The mapping defines a KNN vector field with a specific direction, which is dimension, which is 1536 in this case because we are using Titan embeddings. Now going to orchestrate the function with step functions. Each Lambda here you can see is wrapped in Lambda invoke task, and we chain them route register, the first one, and then the second one is chunk and upsert, then build manifest. The state machine is given the 5-minute timeout, and it's 10-minute timeout, 10 minutes timeout, because the ingestion is bounded. Obviously we expect the deterministic chunking to complete quickly for demo size. We don't have huge files, but you need to make sure that you have enough timeout if your files are bigger. Then the router Lambda is granted permissions. It's granted permission to start the execution of the machine, and then it invoke the S3 bucket and all that stuff that we already have discussed. Now we will move to the online plane. So we define ask API function, which is the Lambda function shown here. It's a synchronous request handler. It is configured with both offline resources and audit resources because it needs to retrieve the latest chunks and write audits as well. It also carries two critical versioning parameters, which are the prompt version and the model name. That is deliberate because if you want traceability, you need explicit version identifier stored at the request time. So we are passing that along with each request. If you later move these into config registry, the idea stays the same. The online plane must commit the prompt and model version into the audit record for each request. Then we define the API gateway. The API gateway is the public front door. We create REST API, define and /ask resource, and wire the post call to invoke the Lambda that we just saw. This gives you stable HTTPS endpoints and decouples the client from Lambda internals. For a demo, I think this is enough, but in production, you add auth, throttling, WAF, and more security around the API gateway because that's your front door. Finally, all the outputs are here. We print bucket names that we created. We print the API URL, the open search endpoint, and index detail. I'm going to run this now. So the deployment is successful, and you can see that the stack has deployed all the resources that we discussed. It has the buckets that we discussed, the DynamoDB tables, our policy, vector collection, the custom function, and the API gateway, state machine, and the policies that we defined. So let's go. I will start by uploading document on our document bucket. So this is our document bucket, and this bucket is versioned. Yeah, you can see the bucket versioning is enabled, and this Lambda function get triggered whenever we upload a new object under uploads folder. So let's start by uploading. Now that I have uploaded the file, I'm going under the uploads folder. I'm going to open the step functions. This is our state machine. So you can see a new execution has started. This is for our offline ingestion plane. It's not a single Lambda. It's a state machine that registers the document versions. Then it chunks the content, generates embeddings, and then upserts vector, and then produces a manifest artifact. So we will wait for this to finish. You see that it has chunk and upsert. That's what is happening right now. Once this would be done, it will invoke another Lambda function. The execution of the state machine has been completed successfully. So now I'm going to open the artifact bucket and go into the manifest folder to see the chunk details and the manifest file that the Lambdas have generated. So we go to manifest. So this is our artifact bucket, and the manifest folder has this manifest. I'm gonna open this. You can see that it has a doc ID, a version ID, and it has 2 chunks ID. That means our document is divided into 2 chunks. So it contains everything that is required, like the timestamp, the document ID, the version ID, and the number of chunks and their IDs. So now I'm going to modify the original document a bit. So I'm going back to the original document, and let's modify it from here. It says the customer support is available via email and web chat from Monday to Friday between 9 a.m. to 5 p.m. I'm going to make it 9 a.m. to 9 p.m. I'm going to save it. Now I'm going to upload the same file to the document bucket again. Okay, so I'm going to upload this file now. So this should invoke another execution of state machine. So let's wait. Yep, so it has invoked and it is completed as well. Now the artifact bucket should have another manifest. Go to the main bucket and manifest. Okay, so it is based on doc ID. We have this one before, and this is the current one. I'm going to open the new one. So let's compare these chunk IDs side by side. So this is our first file, and this is the second one after the edit. You can see that the first chunk remains the same. The ID is identical in both versions. Only the last chunk ID, which was the section which we edited, has been updated, and it has become something from 2cc, and it was 825. This proves that ingestion pipeline is idempotent. Unchanged content, which was the first section, preserve its identity, and only the modify content produces new chunks. So now I'm going to move to the online query part. I'm sending a question to the system, and I'm going to ask, what is the refund policy? This is a question that should be answered from our document. So let's move to that part. I'm going to make a curl request, the post call to the API that we just deployed, and I'm going to ask this question, what is the refund policy? And let's see what it returned. Okay, so here's the answer. Based on the document, it has given us the doc ID and the version ID, which is for us to use. It's literally composed from the chunks that were retrieved from the storage. You can see that the answer includes the document ID, which is the identifier, the version identifier, which tells us exactly which snapshot of knowledge was used to generate this response. That means this answer is reproducible. If I run the same query again in future and the document hasn't changed, I will still get the same IDs because the system is anchored to immutable version. So let's run the same one again and compare the IDs. You can see it has still got the same IDs from which it has returned the response. It has returned us the full chunk because if you remember, we had our document was divided into 2 chunks. So it has given me the first chunk, which means this means I can reconstruct the entire decision path. I know exactly which chunks were used, which model was used, and how the answers were produced. So now we are going to ask another question to the API, which is what is the security policy? Was it let me check in the document. Maybe ask about the customer support. Tell me about the customer support. I want to show you is the audit record. So let's go to the audit bucket, which is here, and go inside the audit folder. We have plenty, like 7 objects, because I tried some questions offline as well. But I'll just open one of these files and see what's inside. So you can see that the audit file has the trace ID, which is the unique identifier to trace the request from end to end. Second one is the question itself, which is how the security incidents are handled. The third one is doc ID, which is the document that was used to generate the answer. Fourth one is the version of that file. Maybe there are so what version is, maybe there are multiple edits to that file. The file was modified multiple times, and each time we uploaded it triggered the step function and it generated a new version. So that's that specific version ID is. And then the retrieved chunks to support the answer, which looks like both of the chunks were retrieved. And then the prompt version, the model, and the output based on this. So the important thing is that now your system is fully traceable. Every decision has an immutable audit record. Every audit record can be replayed, and every piece of knowledge is versioned and also preserved across document updates. So this is a fully auditable AI system which I wanted to cover in this video. To quickly recap what we built, the system is split into 2 planes. One is online and the other one is offline ingestion. The offline plane is responsible for ingesting document, chunking them deterministically, and producing immutable manifests that describe exactly what knowledge exists in the system. The online plane is responsible for answering the questions. It never guesses and it never relies on model's memory. It always retrieves evidence from a specific document version, and every answer is linked to a trace identifier that points to a permanent audit record stored in S3. The important point here is nothing is opaque. Every decision made by the system is explainable, and every answer is replayable, and every piece of knowledge is versioned. So in the next videos, we will cover more real language models, more advanced orchestration frameworks, but the core architecture remains the same. The audit layer, the manifests, and the separation between online and offline planes don't change. That's the foundation you need if you run AI systems in production environments. If you like the video, please like and subscribe to the channel.